So in the last session, we've been talking about conjugate isomorphisms. That is, if alpha and beta are algebraic or a field, then alpha is conjugate, or alpha and beta are conjugates if and only if the conjugate isomorphism exists from f alpha to f beta. And the definition of the conjugate isomorphism goes like this: psi of alpha comma beta of C0 plus C1 alpha plus dash dash Cn minus 1 alpha to the power of n minus 1 is equal to C0 plus C1 beta plus C2 beta square plus dash dash plus Cn minus 1 beta n minus 1. So this is the definition of conjugate isomorphism, and if alpha and beta are conjugate, then a conjugate isomorphism exists. So this is a result which we have been talking about in the last class. We will we'll do an application of this conjugate isomorphism. So let f of x be a polynomial in the ring of polynomial over real numbers, and f of a plus ib is equal to 0 for some a comma b in R. Not every a and b, but some a and b. See, this is a complex number, and this is a polynomial in real numbers. So coefficients of these polynomials are from R. Then I'm going to want to evaluate f of a minus beta. By the way, a minus I beta, ib is a conjugate of a plus ib. So the irregular polynomial, the irreducible polynomial as I over R is x squared plus 1, because I is the 0 of this polynomial, and are the same as the reducible polynomial of minus I comma R. And that implies I and minus I are conjugates. So when I and minus I are conjugate, there exists in conjugate isomorphism I minus I from R of I to R of minus I. But R of I is equal to a plus ib a comma b in R. Let us not write the same a and b. Let's like c plus id c comma d in R. This is because R of I contains the polynomials in I whose degree is less than the irreducible polynomial of I, which is 2. That is why we get this. And this is nothing but the field of complex numbers. And similarly, R of minus I is also same thing. Plus, actually this will be minus ID C comma D in R, which is again is equal to C. So this is actually the conjugate isomorphism. So this is conjugate isomorphism I comma minus I is actually from C to. And what is the definition of the conjugate isomorphism? Psi of A plus IB is equal to A minus, let us take this as CD. C plus ID is equal to C minus I. By the definition of the conjugate isomorphism. See, f of x is a polynomial in R of x. So assume that degree of f of x is equal to n for some n. And f of x is equal to a0 plus a1x plus dash dash an x to the power of n. It's a polynomial in R of x where ai belongs to R. So what is f of a plus ib is equal to a0 plus a1 a plus ib plus dash dash an a plus ib to the power of n, replacing x by a plus ib. And where does this belong to? This belong to R of I or is equal to C. So we can talk about the image of this element by the conjugate isomorphism, because conjugate isomorphism takes an element from C and map to another element in C. So this is I minus I of, I'm going to write it as f of a plus ib is equal to a0 plus, replace a plus ib by a minus ib, because that is how the isomorphism is defined. And because it is isomorphism, you can write it as a plus a minus ib plus dash 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 an a minus ib to the power of n, because this is an isomorphism. And f of a plus ib, we are assuming that is 0. So psi of 0 is actually 0. So this is actually equal to 0. And what is this? This is nothing but f of a minus ib. And that is equal to 0. That's what we want to find out. If f of a plus ib is equal to 0, what is the value of f a minus ib? A minus ib is also 0. So the result is the zeros of polynomials, not just the zeros, it's 0, the complex zeros Complex zeros means zeros that are complex numbers. Complex zeros of a polynomial in R of x occurs in conjugates. Meaning, if one complex number is a zero of a polynomial, then its conjugate is also a zero of that polynomial. Now we will do some definitions on automorphisms. An automorphism on a field E is an isomorphism onto itself. That is, if sigma is an isomorphism from E to E, that implies sigma is automorphism. It's a bijective homomorphism. The next definition is an element A belongs to E is left fixed by an isomorphism sigma on E if sigma of A is equal to A. Meaning, this is E, sigma is any isomorphism from here to any field. And there is an element here, and if you can see the same element here with this map, sigma of A is equal to A. This is mapped to this by sigma. Then this element is called, the element is left fixed by sigma. Meaning this sigma does not move A with this mapping. Now let us consider a set of a collection of isomorphism. Let S is equal to sigma I from an index set, any index set, be a collection of isomorphisms from S, from E, from a field E. And assume that F is a subfield of E. Then F is left fixed by S if sigma I of A is equal to A for all I in I and A in F. That means there is a field E here, there is a field E here, and there is a subfield F here, and there are a lot of isomorphism from going from here to some other field. And obviously there is a same subfield here. Subfield is same. And you have a lot of isomorphism, sigma 1, sigma 2, sigma 3, etc., sigma n. These are all coming from S. For each element of F, B, C, these are all mapped to the same element here. A, B, this is C, this is D. By all of this isomorphism. Then we will say that F is left fixed by the collection of these isomorphism. The collection of this isomorphism. So F is left fixed by S if this condition is true. We will do an example here. Let us take E is equal to Q of root 2 comma root 3. What is Q root 2 comma root 3? It is the smallest field containing root 2 and root 3. And the elements of this field are A plus B root 2 plus C root 3 plus D root 6, where A, B, C, D belong to Q. Now we are going to define a map from Q. Actually, we are going to define the conjugate map. C of root 2 comma minus root 2. That is actually from Q root 2 comma root 3 to Q root 2 comma root 3. This is our E and this is our E dash. And what is the definition of this? The definition of this will be psi of root 2 comma minus root 2 of, take an element from here, A plus B root 2 plus C root 3 plus D root 6 equals, wherever root 2 comes, replace that root 2 by minus root 2, it's conjugate. So that will be A minus B root 2 plus C root 3 minus D root 6, because there is a root 6 here. This is root 6. So what is so there is a field, there is a subfield of this that is fixed by this isomorphism. The subfield field q of root 3 is fixed by psi of root 2 comma minus root. Why? Because if you take, this is our q root 2 comma root 3, there is another q root 2 comma root 3, and we have q here, there is a q here, and there is also a q root 2 here, root 3 here, and there is a q root 3 here. With this map, if you take, see, q definitely is mapping to the same element. Actually, that is by definition of the conjugate isomorphism. But if you take any element here, for example, a plus b root 3, that is not going to change with this isomorphism. That will be mapped to the same field, a plus b root 3. So this whole field is fixed by, the whole field is fixed by the conjugate isomorphism. And that's what we are saying here. Here there is only one, in this collection there is only one isomorphism, and that is our conjugate isomorphism. And F is our q root 3. E is our q root 2 root 3. So every element of q root 3 is left fixed by this isomorphism. In our last example, we took the conjugate isomorphism root 2 comma minus root 2 from q of root 2 comma root 3 to q of root 2 comma root 3. This, we took it as a conjugate isomorphism, but it is actually an automorphism because the domain and the range are same. The reason why we said it is an isomorphism is because it is a conjugate isomorphism. Actually, it is basically originally from root 3 of root 2 to q of root 3 of minus root 2. But these two are same. That is why we considered the conjugate isomorphism from here to here. Now, in general, let S be a collection as, let us say, S equal to, let S equal to sigma I for some I from some index set be a collection of automorphism on a field. So this is okay. then we are going to define a sub collection of elements from E. Either you can say ES or you can say E sigma I, or elements from E such that it is mapped to itself by all automorphisms. Or you can say X belongs to E such that X is left fixed by each of sigma i's. Then what can you say about this collection of elements from E? Is it a field? That's what we are going to find out. See, 0 and 1 belongs to E of sigma I, because sigma I of 0 equal to 0, sigma I of 1 is equal to 1 for all I in I, because they are automorphisms. Now consider two elements from here. A comma B belongs to E sigma I. Then what will be sigma I of A plus B? That is equal to sigma I of A plus sigma I of B, because it's an isomorphism or automorphism, and that is equal to A plus B because A and B are coming from E of I. So that means A plus B belongs to sigma of I. Similarly, A minus B belongs to E of sigma of I. And what will happen? AB, sigma of AB is equal to sigma of A times sigma of B is equal to AB, that belongs to then E of sigma i's. And for B not equal to 0, sigma of A by B is equal to sigma of A by sigma of B, and that is equal to A by B, again belongs to E of sigma i's. So what does that mean? The collection of all elements of E that are left fixed by a collection of automorphism is a subfield of E. Is a subfield of E. And that is what we exactly found in the last example. There Q of root 2 comma root 3, okay, and the collection of the automorphism is only psi of root 2 comma minus root 2. This is our collection because there is only one automorphism there, and that is equal to what? That is equal to Q of root 3, which is a subfield of Q of root 2 comma root 2. And this subfield this subfield E of sigma is called the fixed field of sigma i's. What we found is, if you take the collection of the elements from E, those are fixed by this collection of automorphism, is a subfield of E, and that subfield is called the fixed subfield of the subcollection of automorphisms. In our previous case, we had only one element in the subcollection of automorphisms.